So today, this first lecture is on new architectures for video. So it's going to be deep learning and how new architectures have been proposed and adapted to deal with video sequences. So first, I acknowledge Victor Campos, Amaya Salvador, Alberto Montes, and Santi Pascual, with whom we have explored this topic for quite a while. Also, you have lectures on this talk, a very similar talk, from Victor Campos and myself in the summer school. Okay, so today, the basic task that we're going to tackle is the most basic one for a video, which is called action recognition. It means like, given a video, like the ones that you see on screen, you want to predict a label. So it's video classification if you want, right? So that would be like the Imagenet task for video. And today, like all the results that I show, or almost all of them, they are around this task. Okay? So we take this task because it's kind of the most simple one we can think about for video. Later in other lectures, we'll address other topics like object tracking or video segmentation or other stuff. But today, all the results, everything I present and discuss, just think about this problem. Yeah? Input video, and you want to predict the class label. That's what you have on the top left part of the screen. Yeah? So we want to predict the Imagenet. So that's Imagenet task, but for videos. So that's what you would like. So given a video snippet, you would like to have let's say, top 5 classes or categories, or top 1, and then measure our results based on that. So you see that all results, or most of them, they are on top 5, top 1. This means that it's always a classification problem. So let's think what a video is. Probably Javier already mentioned that, but today probably I think that what's very useful is think that videos are not more than just a sequence of images. We can think about that as a volume, right? So spatial coordinates, temporal coordinates. And we can also think about videos as a sequence of frames, which will later connect us to why on the previous lecture I presented RNNs. You know so far from previous lectures on this master how to deal with still images, at least. So you know that there are several options, most of them or all of them based on convolutions, on convolution neural networks, and that's going to be our starting point. I suppose that you are familiar with this architecture and these models. So the question that arises here is like, okay, so based on what you know on convolution neural networks for still images, and based on the task that I suggested, like given a video snippet, so a sequence of frames, and we want to assign a label indicating which action, which activity is being depicted in that video, how would you solve the task? So now it's an open question for you, right? So how would you solve the task? And if we can start from the simplest option, I would appreciate that, but open question for you. How would you just say that next assignment for you next week, it's fake, okay? You don't have to do it, but just suppose that, but if you follow what we discussed, that's good enough. Okay, so here that's the full list. We covered the first 4 items, and the last 2 are very exotic, actually, or a bit exotic. So I will just briefly mention them, but as they have the potential to be the state of the art in the next 5 years, maybe I think it's good that you know that they exist, and maybe you want to think about them for your master thesis. So let's start with single frame models, because that's the first option that we suggested. So as you propose, one thing we could do is we could fit each frame into a convolution neural network, have our prediction for action recognition, and somehow average, maximum, voting, whatever, combine the predicted labels, and then we have an answer for that. Problems of this approach is that when we do this averaging or combination, we lose total track of the order of the frames. If we do an average or we do any voting, it's lost, right? We don't know the order in which these predictions were produced. There's this first work on video, actually, that's quite popular. It's referred normally as deep video from 2014. And actually, what you suggested is the first option, this single frame solution, in which, like, for each frame I predict something. But in the work, they did something else. Actually, they stack RGB frames. I think that some of you also mentioned something like that. So they stack RGB frames at the, so in this one, sorry. In the early fusion, they stack the RGB frames into a network. The first layer of filters just had more depth, more than 3. And then the fusion, whether was did straight with a single tower of CNN or with different intermediate towers. And there was also another option in which they took the first frame, the last frame, different towers, and the fusion was at the fully connected layers. These are like different configurations that they tried. As you probably can predict, the most exotic one is the one that worked best, but okay, just that you know that this was this first work. And actually, these results are nowadays they are low in terms of performance, but still it's a first step and the easiest one. So if you ever have a problem like this, you can start here, and that should be a baseline to try before trying to do more exotic stuff. In this case, they allow to visualize the filters that were processed here. So you can see now that there are these patterns that they are similar probably to the ones you've seen for visualization on Imagenet, but now they have some motion because they also have the potential to capture motion as well. So that will be the most basic family of algorithms. Let's go for the next one. It will be these spatiotemporal convolutions or 3D convolutions. And you'll see that there are some variations around them. So as discussed, what we could do is, why don't we consider the video as a volume, and then we modify, or we think about our convolutional filters in the first layer as to have one extra dimension. Okay, that's it's difficult to draw if we think about color, but if we think about grayscale, that's fine. So if we consider a video clip represented with this tensor, H, W, and L that would be the chime, we could think about convolutional filters, which are K by K, and this extra dimension, which obviously should be D, should be smaller than the temporal depth. And we could train our filters like on this. In that work, actually, they built clips of 16 frames. That's why I mentioned this number when you kind of propose this option. So they trained that. So in that work, actually, what they were interested is in. So they trained a neural network on this, and then they extracted features that were very rich for many different tasks on video. So what they did is they processed clips of 16 frames. They trained a neural network similar to AlexNet. They extracted the fully connected layer, and they did an average across all the clips of the video. So that's a way. And in this case, they were interested in the feature, not that much on the action recognition task. Okay, and they did a normalization. And then later, with that, they solved different tasks. So they showed that this was a good feature extractor. There was a work later in which I kind of said, okay, maybe, so in between, so that's 2015 and this is 2018. So in between, there were more larger data sets published. Maybe Javi mentioned about video data sets in his class, did he? I'm not sure. Okay, so there's a data set called Kinetics, which is for action recognition, which is quite large, and it was released in between. So as there were much larger data sets at that time. In this work, what they did is they trained 3D convolutions, 3D CNNs, with much more layers, right? So actually, what they did in this work, they say, okay, we've seen that for still images, year after year, the depth of the convolutional neural networks has been increasing, right? So, from Imagenet, VGGs, Google Nets, ResNet, that you reach to 152 layers or so. Could this happen as well with video? And in this work, they said that yes. So you see that thanks to this Kinetics data set, they managed to train a 3D network for classification. Yeah, that's the interesting part. They also introduced residual connections that I'm going to mention later. Then there's another big question here, or interesting question that kind of made a difference at some point, which is, okay, so we have all this knowledge, all these networks trained on Imagenet, on still images, that these features seem to be very transferable, so very rich for whatever reason. And now we say, okay, we would like to work with 3D convolutions because they have this potential to capture the fine-grained differences across time. But training this, it's really computationally intensive. These are many parameters, and probably you need many videos. So just from the previous slide, Kinetics has 300,000 videos. Okay, so this order of magnitude is larger than Imagenet. So Imagenet is 1.2 million, but images. So I don't know how many frames there are in each video, but there are many more, right? So using these datasets, it can be very challenging. And do you think that we could somehow use what we learn, the filters learn from Imagenet, so that we don't have to start training these 3D convolutional filters from scratch? Do you think we could do something there? Do you have any idea? So some trick that would allow us to kind of transfer the knowledge we got from Imagenet would allow us to initialize our C3D network, so that it doesn't start with random weights, but with something that maybe it's already kind of ready to process sequences of frames. Yep. Okay. Yeah. So yes, if you had this idea 3 years ago or so, now you would be famous probably and hired by DeepMind. But that's what they did at that point, and they call that inflated convolutions. But maybe that's the idea, right? So you have if you have a filter that you have trained, you know that it works good, it's good, and now you would like to somehow transfer that to a 3D convolutional filter. So okay, why don't just replicating, stacking that filter for as many times as the temporal depth. Yeah. And this model is called i3D, and that's one of the models that now, if you go on this model ZooS online, you'll find this model available, and many people are using them just to play with video. So it's quite popular. Yeah, I mean, they did many more things, but that's one of the main contributions of this work. What else could you do? Well, hopefully you know about resnets from some other module, and that's an idea that it works for 2D, then why not for 3D? And obviously that actually works as well. And there was this work in which they actually designed a residual 3D network. So here you see that would be like the description of the network on the resnet paper. You see that these filters are 2D, right? And if you look at these other papers with 3D, so they define the residual filters now with a third dimension. And now you see now the sizes they use, and that's the most popular size, is also 3 by 3. Yeah. So maybe if you remember from VGG in that work, they saw that in space, in terms of spatial filters, the size of 3 by 3 was good enough, and actually in time, for the temporal depth, that's also the most common size. In the first paper on C3D, they did this analysis. Yeah. So I mean, in general, so just it's kind of a spoiler, but in general, like everything that you see first on still images, now people somehow bring it into video, right? So that's why. So residual and still images, okay, then somebody tried it on video, and they observe some gains. That's in case you are curious about the gains. So the video would be the still image one, C3D, the original one. That would be like frame by frame with AlexNet and GoogleNet, so 2D. And this Res 3D, it was improved a little bit more the performance. Also, so that you have an idea in terms of computation, like how hard it is to use 3D convolutions. Here you have an analysis comparing the ResNet 18 layers and 34 layers on 2D with their equivalent with 3D convolutions. And here you see a gain in accuracy, right? So 3D versions, they perform better than the 2D versions. But also notice like the amount of parameters, it's kind of multiplied by 3, right? And that means in terms of computation, that's quite a lot. And maybe it's not worth it, right? Maybe it's not worth it to have so much more computation for this gain of accuracy. These are trade-offs that if you ever need to deal with that, you need to be aware. Yeah, but it's not always accuracy what matters. And especially in video, like normally companies, they want, in many cases, they want real time, right? And that's the kind of things that you must be aware of. Good. More variations around the idea of 3D convolutions are what's called mixed convolutions, which is such a simple concept of combining on some layers you use 3D convolutions, and in some other layers you switch to 2D convolutions. Yeah. So they did this work. Basically, the idea here was try to reduce parameters in the total size of the network without trying not to lose much accuracy. Yeah, that's what they're trying to do. And they tried both options, like first 3D, then 2D, and first 2D and then 3D, both options. Now you'll see the results. So compared to what would be like the classical residual 2D, residual 3D, 3 times parameters, if we have, so MC is first 3D and then 2D, this MC, okay. The reverse one has an R, sorry. So best performance is over here. So it would be like MC, so first 3D and then 2D in terms of performance. And that's the amount of parameters that you obtain. So just notice that you have this amount of parameters, and you compare it with the 3D, right? Performance is, if you compare this one and this one, that's better, and the amount of parameters is much smaller, which is pretty cool, right? Also, if you try putting the 3D convolutions at deeper, which normally like you have like more depth channels, that also like increase a lot the amount of parameters, and they didn't observe so much gain of performance. So actually, like if you ever wonder what's better, it's better to first put the 3D convolutions first and then the 2D. Yeah, and you can have like better performance with less parameters, which is always what we want. Yeah. More variations on the idea. Why considering the same way the spatial and the temporal dimensions? Maybe they have something similar. Why not, let's say, first learning convolutions in time and then convolutions in space? And that's what they explore in this work, which is also one of the most popular ones nowadays. So why not transforming our 3D convolutions? In this case, okay, they changed the name of the letters, but it would be the time and the 2 spatial dimensions. Why not first having the 2D convolutions? So first you learn that, you have, let's say, one layer on this, and then at the output of these features, you run the one by one by T, by depth convolutions. Yeah. If you do that, you're going to be using less parameters. If you think about it, it's less parameters to have like 2D and then 1D than just to have a whole cube, right? And you still have the potential to reuse features across time, so maybe it works. And if you wonder if that's a good idea, so yes, it's a good idea. You have the result is here on top. Yeah, that's the R2D one. The R is because there's residual connections as well, but it's best accuracy. And so here you have the computational power. So with the comparable computational power to these ones, which are the other options that we consider. So you have all the options, like only residual, the mixed convolutions, the reverse. That's the best one if you look at comparable computation. Yeah. Okay. And that's many of the variations. As you can see, like with one idea, you can start playing with many variations. What if we compare? What if we combine 2D convolutions with recurrent neural networks, just for the idea of trying to reach farther in time. Recurrent neural networks, so on Tuesday, they have this potential of remembering things they've seen in the past. And I also show you this slide. So it is like for each frame, we will extract features with CNNs, and then later we feed that into a recurrent neural network. Okay. Also, just today, I'm not going to show you an example, but don't take the idea that one layer should be convolutional or recurrent. Okay. You could have layers which are convolutional and recurrent at the same time. So convolutional filters that remember what they have seen in the past. That's possible. Okay. I think I have not seen this for the task of action recognition, but in other tasks I have seen it, and we'll see it in future lectures. Yeah, but don't take the idea that one layer must be convolutional or recurrent. That's not true. You can have convolutional and recurrent layers. They are just filters that remember what they have seen in the past. Convolutional filters that remember what they have seen in the past. Okay, let's go back to CNN and RNN. So here, that's this table from that same paper from Res3D, which actually they did a very exhaustive analysis of what happened with residual 3D convolutions, and actually they compare it as well with models that combine features extracted with AlexNet or GoogleNet, combined with some LSTMs that would be like the currency, and this component would be like some kind of putting on the convolutional level. So you see that in this case the results here are also pretty good without the. So these are not 3D, right? So if you compare like LSTM, so it's really basic in these two ones. These results are pretty good compared with the rest 3D that I showed earlier. So it's not a bad option, okay? And how could we? So okay, based on that, having 2D convolutions and LSTMs has the potential to perform really well, like this one, for example. So this was a kind of a residual resnet, right? And this GoogleNet, which is previous from resnet. Do you think that there could be a way to combine the benefits from 3D convolutions with the benefits from recurrent neural networks? So having this capability of capturing like these short-term changes combined with the potential of RNNs of capturing longer-term changes, how could we do that? Okay, so how many of you think you are lost in the lecture? Okay, I guess, okay. Yeah, sorry, I should do pause. How many of you think that are following the lecture fine? Okay, that's half, okay. Then, based on what I have, so here I'm kind of saying, I just show you one table in which they'll say, okay, if you have this residual 3D convolution, you have these results. If you combine the features starting from 2D convolutions like GoogleNet, you feed that into a RNN, results can be better, but these are like 2D convolutions. Yeah? Do you think there's some way in which we could maybe combine the best of both worlds, best of 3D convolution niche families with longer term? Yes, Oscar.
You could split your video like in clips of 16 frames, process that with 3D convolutions, with the 3D convolution algorithm, and take one of the feature maps of the output or feature layers, take that as input at each time step of a recurring neural network.
Yeah, so what Oscar says, yeah, so you use C3D as a feature extractor. So actually, earlier when I just show you actually the model, the basic model from 3D, this one, I presented it as a feature extractor. Yeah, so they train it for, I think, to classify sports video, 1 million sports video snippets, but they kind of use it as a feature extractor in the experiments. If you look at the paper, and at the end they obtain like this feature of 4K dimensions. And what he's suggesting, like, just take these 4K dimensions and feed that into an RNN. So it would have the potential to kind of model longer-term dependencies between clips of 16 frames. Yeah, so then you have the potential to have the best of both worlds. Okay, so actually that's what we tried here at UBC some years ago, and it worked, well, it worked fine. I think it was like a kind of smallish work, but actually we got an award in a NeurIPS workshop, actually, because I think it was a moment in which we really combined the two methods, right? So we have our video clips, 16 frames clips, we extract our 3D features, and we feed that into an RNN, right? And that was a work mainly from Alberto Montes that was awarded in this workshop on NeurIPS. There's also another work we had here at UPC in which we try to make more efficient this architecture of CNN and RNN. So if you try to, let's say, still solve this problem of action recognition in a video, with this approach of RNNs and CNNs and RNNs, like the naive approach is like I extract CNN features for all my frames, I feed it into an RNN, and then I train an RNN or do my inference. In terms of computation, the part that inference time, especially, in terms of computation, what takes most of the computation is the extraction of the convolutional neural network features. Yeah, and we asked, well, actually Victor Campos, he asked, okay, this is really very hard computational, very demanding. And maybe it's not necessary, right? If you want to say if one video there's somebody throwing a boomerang, maybe you don't need to look at each and every possible frame of the video. Okay, maybe it would be nice if the network learned when to look at the video. Maybe it doesn't need to process all the frames. So most people, what you do, the naive approach is you do a subsample, so you take maybe 1 frame per second or so, but we want to do something adaptive to the complexity of the task, and to make it learnable. So that's what we did. We proposed a model called SkipRNN, in which what it does is that the model decides how many input samples to skip. And we apply that for video, but we also apply to other problems. Yeah? And the goal here is like to obtain the same accuracy, or just not to have much loss of performance, but with much less computational effort. So, for example, what we did in this example, in this dummy example, we solved Mnist. So, have you played with Mnist in the module? Do you know it? So, Mnist is a classification, the most simple classification benchmark. There are handwritten digits. Yeah. So we solved Mnist like flattening all the pixels. Yeah, and then processing each pixel with an RNN. So it's a super bad idea if you want to solve Mnist. Okay, but it's very good if you want to show how this works. But it's possible. You can do that. You can flatten your Mnist and feed that in an RNN and ask the RNN to predict what digit it was after seeing all the pixels, even if they are flattened. It's possible to be done. Okay, so we did that, and then what you see here in this figure is how our model learned to skip pixels, looking at pixels on Mnist. So in blue, you see the pixels that the model did not look to classify the Mnist, and you see it across different training epochs. So the more it's trained, the better the model learns how to skip samples. So if you see at the very end, when you reach around 95% of accuracy, mostly the pixels on top, the model learned that there's nothing interesting on top of Mnist, because normally the handwritten digits are kind of centered, right? So it learned how to skip that, and then depending on the image, it adapts to the image to decide how many pixels it should skip. Yeah. So this concept then we also apply to video, and you see like for action recognition, red frames means that the model decided to skip that frame, and it only observes the ones that you see in green, which are just a few of them, to solve the task of action recognition. Yeah. So finally, combining RGB with optical flow. How can you do that? You propose to stack, and I said that I think that not many people does it, but that it's a bug. So first thing, optical flow. I don't know if you saw this, but that's what optical flow looks like. So these algorithms that predict like this displacement of the pixels. And there are many handcrafted algorithms that do that. And you have here a list of them, and that's going to be useful later for your project because you're going to need to process this. Okay. Actually, there are neural networks that compute optical flow, but basically they are neural networks that were trained with optical flow computed with one of these algorithms, which is something you can do. But that doesn't mean that the neural network is actually computing the optical flow. Okay? It means that as it's a regressor, if you want, they are very good regressors. They can predict very good optical flows, but they are not really computing displacement between pixels. Yeah? So if you see neural networks that predict optical flow, it means that they are not actually computing the displacement of the pixels. They are predicting the flow based on the training data. And they do it very well. Then, assuming that you have the optical flow coming from wherever, from a handcrafted algorithm or from a deep neural network, classic option is you have two streams, it's called, right? So in one stream, you feed your RGB data, spatial stream. In another stream, you take the neighboring frames, you complete the optical flow on these neighboring frames, and you feed that as an input of a different and independent stream. Yeah? In the first proposal, what they did is they were classifying the action for the spatial stream, for the temporal stream, and then they just fused the class scores. That was the first approach, the first time that this approach was adopted. Some years afterward, another similar approach, they did the fusion not at the class predictions, but at features predictions. So at some point, they combined the feature maps before predicting the class, and that improved the results. Later, some years later, there were residual networks were introduced, and actually, like these intermediate features, you see these red arrows here, they were also transferred from the motion into the appearance stream, which I guess not exactly what Oscar was suggesting, but it's kind of similar. Okay, they were just fitting the features there, but it's not really computing optical flow on the features. It's kind of early-ish fusions of features. Then that word that I mentioned earlier on inflated convolutions, I3D, it's one of the state-of-the-art, but actually it does these inflated convolutions to start training, but also it feeds, it's a two-stream network where you have optical flow and 3D convolution. So it's pretty heavy in terms of computation. It works very well, but it's heavy on computation. And I have here all the list of the most popular architectures, so you can compare. That's taken from this paper. You can combine everything. You can have the RGB with the optical flow and RNNs. I mean, you can do everything all together, right? Nothing prevents you from just keep stacking things, and this has been done as well. If you wonder if can we just skip the two streams for optical flow? Yes, that's this recent paper, but they did something a bit more complicated actually. So this is called one stream RGB and optical flow. So they 2-in-1 networks it's called, but they actually fed the optical flow at intermediate layers of this main network, let's say, and they combine like some features extracted from optical flow. Yeah, but again, it's like different ways to combine RGB with optical flow. This can get very complex or more simpler, but in general, you get extra performance, but at the cost of extra computation. So computing extra optical flow, it can be costly. Here you see in this work how the features before the optical flow modulation were modified. Okay, I think we're almost out of time, but if you compare what would it be like if you compare the two stream with the 2-in-1 stream, like doing this fusion optical flow? They observe gain in this task called action detection. Action detection means like it's not action recognition. It means like there's this action that starts here and ends here. Okay, but action classification actually didn't work better. So there's this option, but it's not clear like how better it is. But also the number of parameters it's much lower, because now we only have one stream. You don't have two streams. So that's also something to be taken into account. Yeah, there are trade-offs everywhere, just that you know. Then, just to finish super quickly, the two exotic names, or that might be state of the art in the next 5 years. First of one, this one from Facebook, that's called dual slow and fast frame rates. So basically, what it means is we are trying to capture these longer dependencies and shorter ones with two different networks. One of them that works at very low frame rate, like in the paper 2 frames per second. But this network has quite a high capacity. It means it has like many parameters. But on the other hand, they have another network that it runs at 16 frames per second. So it's very high frame rate. But as there are like so many frames, here the model has much lower capacity. They reduce a lot the amount of filters and layers and everything. Yeah? And by combining both, that's the state of the art nowadays. Right? If you just, that's a final table that I think that's more or less state of the art. That's what you, that's where you get the best results. And it's quite, if you look at the numbers, so it's almost like at the 80. So that's kind of the state of the art, and models are publicly available. So if you want to do things with video, maybe you should start looking here. Also, they also released something later in which also added audio in case you want to mix video with audio. Just to finish, just brief notation. So there are some new-ish architecture called Capsule Networks that were proposed from Geoffrey Hinton, and they are quite demanding in terms of computation, but in terms of accuracy, people are obtaining very good results. Okay, so if you look at this work, you see that they also have very interesting results, but it's hard to compute all this. But you see that in other tasks, normally you also see that video capsule networks, that's the name of these layers that I'm not going to present, but they achieve good performances. If you want to play, here I added links to the couple of PyTorch implementations for the most popular models and modern models. And if you want to know more, just come tomorrow and I guess ask Francisco about Torch Vision, about these models. I guess he might give you some more ideas. Yeah, suggest that you read this if you want. These are like slides that actually from lectures that we will see in the future, so I guess you don't have to worry much on this. But if you are very anxious about future lectures, you can start looking at them. This will be it for today.